All right, so welcome to today's Mathematics 1 lesson. Let's turn this up a little. All right, please take your seat so we can get started. Maybe a little more. Good. So you've all found the room, apparently. It's smaller than I remembered that, but there are still a couple of seats left, so I hope you should all fit in here. Livestream also seems to be working, so let's get started. Now, to start you off, I have prepared a quick quiz. As usual, you're welcome to log into TweetBack and answer this little question here. Is the intersection of any two linear subspaces of R to the n always contains the origin? Is that true or is it false? All right, I'll give you 20 more seconds, and then we'll take a look at your answers. All right, so let's see. Here's what you answered. At least the majority said true. A considerable amount said false. Now you hopefully do remember the first step in checking whether a set is a linear subspace or not. And that was checking whether the origin is contained in that set, right? If the origin is not in the set, it can't be a linear subspace. And that of course means every linear subspace contains the origin. And if I take any two linear subspaces, they have at least the origin in common. So that means their intersection also contains the origin. Right? So the correct answer would be true. All right. Then let's take a look at today's slides. Here we go. We've talked about vector spaces, and we've also talked about linear subspaces yesterday. And I already told you the main idea of all of this, at least for the moment, is to be able to characterize or describe the solution sets of systems with linear equations. And this is what I've talked about in this presentation 20 here, solution spaces of SLEs. Because as it turns out, and this is basically the main theorem here, the solution space for a homogeneous system of linear equations is always a linear subspace. And if I have n variables, then of course all solutions live in the R to the n space. So it's a linear subspace of R to the n. So that's basically the take-home message here. For a homogeneous system of linear equations, so right-hand side is 0, the solution set is always a linear subspace. And that is one important reason of why we're interested in linear subspaces. I'm not going to go through the proof. You can watch it in a video if you want to. Yes? a subset and a subspace. Let me go through that part first, and then I'll come back to your question, okay? All right, so here's an example of linear subspace, and maybe that's part of the answer to your question already. In R2, so in the plane, and that's the easiest case if you want to visualize something, usually use the plane. There's basically three kinds of linear subspaces. The first two are the trivial ones. So the origin itself, we've already said, any set that contains just the origin, just the zero vector, is of course a linear subspace. And the vector space itself, trivial, that's also a subset of itself, so it's a linear subspace. Right? So those are two possibilities. And in R2, all the other possibilities are these, of this type here. So you have lines through the origin. So if I have the plane here, and I want a linear subspace in that plane, and let's say I want that subspace to contain a certain point, which is not the origin, to make things a little more interesting. So let's say I want it to contain this point here. How does the subspace look? Well, you do know that for a subspace, it must not be empty. This is obviously not empty. It contains at least that one point. And you do know that for any vectors in the subspace, all multiples, all scalar multiples are contained in the subspace, and all sums of any two vectors are contained in the subspace. Right? So the space needs to be closed with respect to that. So what do we need to add? Well, if we consider this vector here, then first thing we need to add is all scalar multiples of that vector. So we can shorten it, we can lengthen it, we can flip it around by multiplying it with a negative scalar. And we need to include all of these to get a vector space that contains that point. Right? So what we'll have to do here is we'll include all the points on this dashed line. Imagine it would be a straight line, actually. And of course, also in the other direction, we need to include all of these points as well, right? So that line here, we get that by just scaling the original vector. Now, is that a vector space already? We've talked about that yesterday. It does contain all scalar multiples. Does it also contain all sums of any two vectors? Well, it turns out, yes, it does. Yeah? If you take any two vectors on that line, like this one and then this one, and you add them, the direction always is the same. It might turn in the other direction like that, might flip around, but it always stays on the line. So if you take this and then subtract this, for example, you're getting there. If you take this and add this, you're getting somewhere here. So you stay on the line, right? Addition works, scalar multiplication works, and of course that thing is not empty. And obviously it contains the origin. Right? That's simply due to the fact that you need to have the zero multiple of that. So if the scalar is 0, then that needs to be included, and 0 times any vector will always be the origin. So that needs to be included in the space. All right? So if you want a linear subspace of R2 that contains a given point, you'll end up with a line through that point and through the origin. Or, of course, just the origin if that's where you start with. Okay, so that's the third possibility. If you want to include 2 points, let's take a look at that maybe. So let's say I also want to include this additional point here in my vector space. Then we've just learned that I'll have to include the line through this point and the origin. So that's what I need to include. And then I also have to include sums of any two vectors. Well, as long as I stay on one of those lines, I'm good. So let's take a look at like one vector from this line and a different vector from that line here. And if you want to add those two together, basically we visually place one arrow on top of the other, like that. So here's where we end up. And that means, well, let me maybe write this in yellow here. So this is our new point. And as the sum of any two vectors must be included in the subspace, that means the yellow point must also be in the subspace, right? And when I have that yellow point, I also need to include the line through that yellow point. So I get this. And I hope you can see that I can continue with this, choosing different vectors from those two lines. And basically what I will get is anything in that plane. Yeah, with those two lines, vectors on those two lines, I can reach any point in the plane. And that means if I want to include two different points, none of which is the origin, I'll end up with the whole plane. There's nothing in between, right? So that's the three possible cases. Just the origin, any line through the origin, or R2. In R3, just to add that quickly, things are similar. So the cases in R3, again, of course, you have the origin. The next possible case is any line through the origin. Same argument as here in the plane. Also works in three-dimensional space. Then if I take 2 points and 2 lines through the origin, well, I need to include everything that is generated by those 2 lines, right? And these 2 vectors here, I need to include everything I can get as a sum of those 2 vectors, right? So that is everything that is on the plane spanned by those 2, right? So what I get in R3 is this whole plane. So now I have one more step, right, in between the lines and the whole space. So the next step would then again be the whole space. So if I add another point that is not already on the plane, I get R3. And of course, similar arguments can be made for higher dimensions, right? You get, for each dimension more, you get one space more in between. All right, does that answer your question? Maybe not. Did that answer your question? Good. All right, so here's the possible different subsystems. And well, what that means is those are the only possible solution sets to systems of linear equations, right? You can either have the origin, homogeneous, right? You can either have the origin, you can have a line, you can have a plane in R3, you can have the whole space in R3 or in R2. And of course, things continue similarly in higher dimensions. We'll try to describe the structure of that set in a more concise way in just a few minutes. Let's quickly talk about inhomogeneous systems before that. Of course, often the right-hand side is not 0, so what do we do if the right-hand side is not 0? So we have the inhomogeneous case. Well, the claim is it's almost the same thing. The claim is you can first solve the homogeneous case. You get some subspace, let's call it U. That is a solution set for the homogeneous system. And then you find one single solution for the inhomogeneous case. No, it's not just one single solution. Guess one. And then I claim the whole set of solutions is given like by this expression here. So this S bar, this is one single solution of the inhomogeneous system. And the whole set is simply given by S bar plus U. So that means you take this S bar, you add any possible U in this linear subspace. And what that means geometrically, oops, wrong color, just a sec. What that means geometrically basically is you're starting with the subspace here. Let's say we have a line through the origin. Let's say this is how U looks like. Well, then what is S bar plus U? Well, you're translating this whole set by a constant vector. Let's say this here is our S bar. Then S bar plus U simply looks like this. Right? So we're taking that linear subspace and we're translating it by S bar, by a particular solution of our inhomogeneous system, and that's the whole solution set of the inhomogeneous system. And you can see this is not necessarily a vector space. It doesn't include the origin in most cases. It might, but doesn't have to. But it almost has the same structure. It's just a translation of a vector space. Yeah, so you can treat it almost the same, but you'd have to translate it first. And that's what we call an affine space later on. We'll take a closer look at affine spaces next week, just to mention that already. So an affine space is basically a vector space that has been translated by some constant vector. All right, and just a quick look at the proof. Why is this the case? Well, if I have the set of solutions for the homogeneous system, then let's take any equation in the system, so any row I, and try to substitute S bar plus any solution in U into that system. It looks like this here. So instead of x1, I write S bar 1 plus U1. Instead of xn, I write Sn bar plus UN, and so on. And I just rearrange that a little. I collect all the S bar expressions here, and I collect all the U expressions here. And what I get is, well, U solves the homogeneous system, so this is 0, because the right-hand side of the homogeneous system is 0. And S bar solves the inhomogeneous system, so this is BI. And that means for any U bar in that space here, for any U bar in U that I can add to my S bar, I get a new solution. Right? So that all solves my inhomogeneous system. And that's the first part of the proof, showing that, in fact, all vectors in that new set, S bar plus U, actually solve my inhomogeneous system. The second part is to show that this is everything. There is no other solution. And that's this, the second part here that we're looking at. So consider any two solutions, right? T bar, S bar of the inhomogeneous system. Then what I'd like to show is that, in fact, T bar has this precise structure here. So there is some U such that T bar is S bar plus U. So it's already contained in S bar plus U. Right? And to see that, I solve this expression for U, I get this. And then I just need to prove that this U actually is a solution to the homogeneous system. And again, I can just do that by substituting that solution here into any of the equations, doing the computations, and again, reformulating a little. I collect all the T bars, I collect all the S bars. I get BI here, I get BI there. And the difference is, of course, 0. All right? And that proves this structural result here. Okay, so that means the solution space of an inhomogeneous system of linear equations is obtained by taking the solution space of the corresponding homogeneous system and adding one solution. All right, so now we know that. Let's take a quick look at, what do I have it? Let's take a quick look at exercise, I think it was 2.4. I should have sheet 2 somewhere right here. So you hopefully remember that exercise 2.4. We've just talked about that last Thursday in the exercise classes. Specifically, I'd like to take a quick look at this one here. Let's see if I can just copy that into my notes. Copy. Yeah. Yep, that's what I want. And here's my notes for today. Great. Okay, that question. And you remember that we solved the homogeneous case, this one. We've discussed this in class last week. So the task is to come up with a system of linear equations that is solved by this solution set. And now that I know the connection between homogeneous and inhomogeneous, what I can do is I can try to come up with a system of linear equations that has just this solution set, because this is the linear subspace. So there must be a homogeneous system solving that. We've discussed that already. You remember that we did that in class last week, and we came up with this system of linear equations for that. Let me briefly copy that. All right, and let's erase all that unnecessary stuff here. Okay, so that's a homogeneous system of linear equations. Such that the solution set is, let's call it U, is given by 1, 2, 3 times lambda and lambda in the real. So basically the line through the origin in direction 1, 2, 3. And now if you want our solution, our system, no, let me start again. If you want a system of linear equations that has this solution set, and we know the solution set of an inhomogeneous system looks just like this, a particular solution, one single solution of the inhomogeneous system, plus all solutions of the homogeneous system. So that has exactly the structure you want. That's our S bar, and that's our U. We already have a system that produces U. We just need to make sure that this here is a solution of the inhomogeneous system. So let's take the system we have, make it inhomogeneous in a way such that this is a solution. All right? Well, that's what we're going to do. So to make it inhomogeneous, we modify the right-hand side. Such that this vector here, -1, 3, 1, solves the inhomogeneous system of linear equations. Well, how do we modify the right-hand side? Well, let's just see what we need. We can just take the solution, substitute it in those two equations, see what the left-hand side is, and then just use that as right-hand side. So to make sure that this solves the system. Right, so what we do is we'll substitute this -1, 3, 1 into the left-hand side. And what we get, -2 times -1 plus 3 plus 0. That is, let's see, +2 plus 3, that should be 5. And here, the second equation, this one here, we had 0 minus 3/2 times 3 plus 1. So that is 9/2 plus 2/2. So that's 11/, no, sorry, that's a minus, not 11. So that's -7/2. Okay, and that's where we get our system of linear equations. we just copy the homogeneous system, modify the right-hand side, using these two results here. So we set a 5 here and minus 7 over 2 here. And then what we get is U solves, or is the solution space, I should write that, is the solution space of the homogeneous system of linear equations. And we've also made sure that minus 1, 3, 1 is a solution of the inhomogeneous SLE. Right? And that means the solution space of the inhomogeneous SLE is exactly as we want it to be. So the solution space of this inhomogeneous SLE is minus 1, 3, 1 plus U, which is exactly the set we wanted. Right? So that is probably the most general approach to attack problems like this one. First do the homogeneous case, then modify your result to make sure that this one particular solution works for the inhomogeneous case. And the theory gives you all the rest. All right. Questions at this point? Otherwise, we'll go on with more topics. All right, so now we know why we want to look at vector spaces and linear subspaces of R to the n in particular. Next thing on our list is we want to be able to have a concise, compact description of these spaces. And we want to be able to have possibly very few simple characteristics that tell us how these spaces look like, more or less. And the first step in that direction is to talk about linear combinations. The basic idea of a linear combination is pretty simple. So you have a vector space, or it could be a subspace. You have a couple of vectors, finitely many. Well, this R in n basically says take finitely many, any number you want, but finitely many. And for each vector, you have a scalar. And then what you do is we just multiply each vector with its associated scalar and sum it all up. And any expression that looks like this is called a linear combination of that vectors. Okay, so just a fancy name for that, sum. And then we say we frequently need the set of all possible linear combinations of a set of vectors. So that will also get a name, and we call that the span. Right? So for any subset, any finite subset of vectors, the span is defined as all expressions of these vectors that look like this, all possible linear combinations. Take all possible multiples, take all possible sums, that's the linear combination. That's the linear hull or span. Basically, you remember that we just did that a couple of minutes earlier when we've talked about the vector spaces in R2. Right? You hopefully remember we had this vector here and this vector here, the two orange ones. And then the question is, well, what is the smallest vector space that contains those? And we started by taking all multiples of those vectors, giving us these two lines, and then we took all sums of vectors on these lines. And what we did here is we computed the span of those 2 points. It's just that. Yeah, on the span of this 1 point here alone, we also did that before, that yields this line here. Okay? So you could also say the question is, given this set M of vectors, what is the smallest linear subspace that contains all of these? That's the span. And then just for convenience, we define the span of the empty set to be the vector space that consists just of the 0 vector. Right? Again, you could say this is the smallest vector space that contains the empty set. Of course, every other set contains the empty set. And that's the smallest possible set that is also a vector space. All right? Couple of examples. So let's say this here is our set M, 3 vectors. And then we can just take arbitrary coefficients here, compute that sum. That's the result, and that's a linear combination of those 3 vectors. So of course, any linear combination is contained in the span. Right? So that is one element of the span. And now to find out what the span is, well, how do we actually compute the span? Or maybe as an intermediate step, how do we find out if any given vector is contained in the span? Well, that last question can simply be answered in this way. So given a vector, b1, b2, b3, we want to find out whether that is contained in the span of M. Here are the vectors in M. Well, if it's contained in M, there must be some linear combination that yields exactly this vector. So there must be some lambdas such that this is true. And if you just read this row by row, you see this is actually a system of linear equations. All right, so the first row is lambda 1 times 1 plus lambda 2 times 3 plus lambda 3 times 4 is b1. And you get the same thing for the other 2 rows. So that means what we have here is 3 equations, and the variables are now the lambdas. And of course, we can try and solve that. And if there is a solution, well, then there's the lambdas. That means the right-hand side, this b, is actually contained in the span. If there's no solution, then it's not contained in the span. Right? So, well, we can just do this by putting it into Blow form. And then we can take a look at that and see when there is a solution. And well, you can either just try and solve it, or you can try to find out the rank and then see if you can prove there is a solution. You don't actually need the solution. You just need to be sure there exists one or not. Right? We don't want to have this linear combination in hand. We just want to make sure there exists one. Possibly more than one. That's fine. Yeah, it doesn't have to be unique. All right. So that's the span. One more example here. These 4 vectors, if we start with the first 3 of them, take a look at that, and you'll see that this is already a matrix in echelon form. We have 3 pivot elements here. And that means, well, for every right-hand side, we can find a solution, no matter what right-hand side we are using. Well, what does that mean? Well, every vector in R3 is contained in the span of those 3. And that means their span must be the whole space R3. Right? That also means this last vector here, we don't actually need that one. It doesn't add anything. You can't add any more. We already have the whole space, right? So this is redundant. We wouldn't have needed that. And we can easily remove it to get the same span. And that leads to the next definition. Thanks a lot. All right, so that leads to the next question of linear independence. Basically, the question here is, given any set of vectors, are there redundancies in there? Now, before we do that, let's maybe have a quick look at homework H32. Let's see if I can get a sheet here. Yep. So here the question is, given a vector space defined as the span of two vectors, these two, are the following vectors contained in V? What do you do to find that out? Well, same thing as we just did. You try to solve a system of linear equations. If there is a solution, they're contained in the span. If there's no solution, they're not contained in the span. So I trust you all did your homework. So let's have a look on Tweetback and see what your results were. Let me just see. Yeah. And just out of curiosity, I'd also like to know how hard you found that problem. All right, I'll give you another couple of seconds to answer. And then let's take a look at the results here. So most of you saying that the second vector is contained in our span and the other two are not. And that is actually the right answer, of course, right? So B is contained in the span, A and C are not contained in the span. And I surely hope you didn't find that too hard. Let's see. Oh, well. Quite a few on the hard side here. But I'm hoping some practice will take care of that. All right, so let's talk about linear independence. So if you could please quiet down again so we can go on. Right, linear independence. So I already said, given any set of vectors, the question is now, is there something that is not actually necessary for the span, right? Is there vectors that can be removed without changing the span of the set? And that is basically the origin of that definition of linear independence. And that definition looks a little complicated. Mainly, the reason for that is that we want to cover all possible cases with just one definition. And I'll try to explain, I'll try to motivate that later. So, given any set of vectors, that set is called linearly dependent if we can find a linear combination of the zero vector. So we can use these vectors to combine the zero vector without setting all the lambdas to zero. Of course, if you set all lambdas to zero, you'll always get the zero vector, no matter what the v's are. Now, if there is another possibility to do that, then the v's are called linearly dependent. And what that means is, if there is another possibility, let's say you have this lambda 1, v1, let's say we just have maybe 3 vectors, and there are lambdas such that this is 0. And not all of these lambdas are 0. So let's say, for example, we know that this lambda 2 is not 0. Then that means we can solve this whole thing for v2. Right? So if that's the case, we can say, well, then v2, then v2 must be, well, let's take those on the right-hand side, minus lambda 1 v1 minus lambda 3 v3. And then we have to divide by lambda 2, and that's why we want it to not be 0. And that means we can express v2 as a linear combination of v1 and v3. So we can just throw away v2, the span is the same. Right? v1 and v3 can do everything that v2 can. But of course, that only works if we know which of those lambdas is not 0. It might not work for all the vectors, right? So for example, maybe lambda 1 is 0. Then we couldn't solve for v1. And that's why the formulation is like it is. Basically, the idea of linear dependence is to say, well, I can solve for one of the vectors in that chain. I can express that as the sum of the others. Point is, I don't know which one that is. It might not work for every vector. And that's why we're using this seemingly a little more complicated definition, because then it doesn't really matter. Right? Zeros here are fine as long as it's not all 0. All right? So in R2, for example, that whole thing is really easy. If you have vectors in R2 that are linearly dependent, what do they look like? Well, in R2, linear dependence means you have something like this, right? So lambda 1 v1 plus lambda 2 v2 is 0, 0. And not all of these are 0, all of the lambdas. Well, obviously, then none of them can be 0. Right? If one is 0, then let's say this would be 0. Then I have lambda 1 v1 equals 0. Well, either v1 is 0 itself, because that might be the case, or lambda 1 would have to be 0 as well. So let's exclude the case that one of those vectors might be the 0 vector. If they're both non-zero, then none of the lambdas can be 0. And then that means I can solve for any of these. For example, for v1. And then this is minus lambda 2 over lambda 1 v2. So in other words, v1 is a scalar multiple of v2. Right? So in this case here, it's really easy. You have one vector, and any linearly dependent vector is a scalar multiple of that vector. So this one, or any other vector on that line that would be linearly dependent. And please remember, if we're talking about linear dependence or independence, we're always talking about sets of vectors. A single vector it doesn't really make sense to talk about a single vector and say this is linearly dependent or independent. It's not. We're always talking about a set of vectors. And of course, that might be a set that just contains one vector. But you wouldn't say something like V1 is linearly dependent on V2 or something like that. You would say the set of V1, V2 is linearly dependent. Please remember that. All right? Now, what is the more interesting case for us is not linear dependence, because if I have linear dependent vectors, that means I can throw away at least one of those without changing the span. What is more interesting is the case of linearly independent vectors. And that means, well, basically the opposite. That means this here can only be solved by setting all the lambdas to 0. There's no other solution. Then I call the vectors linearly independent. And that means none of those vectors can be expressed as a linear combination of the others. Or in other words, throwing any of these vectors away will change the span of a set. Yeah, so in this way, I have an irredundant description, an irredundant basis of that set, an irredundant generator. And that is the main idea of this linear dependence and independence. All right, quick remark. If we're talking about systems of linear equations, we can consider the rows or the columns of that system as vectors. And we can, of course, ask the question, are those rows or columns linearly dependent or not? And if we do that, I think I have an example of that somewhere. Do I? Nope. Well, let's make one up. If I do that, let's say we have a system of linear equations in row echelon form, like this one here. It's not row echelon form, sorry. One needs to be a 0 here. Let's make this a -2 and a 1. Let's say it looks like this, right? And what do we have here? Here's our staircase. Here's our pivot elements. And my claim is all the rows with pivot elements form a linearly independent set. Same thing for the columns. All the columns with pivot elements form a linearly independent set. Why is that the case? Now let's look at the rows first. So you have the rows. I just transpose those. So I'll write this first row in column form. And then the second row in column form. And then the third row in column form. Right, here is our pivot elements once again. And now to see whether those are linearly independent, well, I need to put coefficients in front of them. Take this linear combination and ask, can I get the 0 vector from this, and is setting all lambdas to 0 the only possibility to do this? What I can do now is I look at the pivots, right? So this first row here, this corresponds to the equation lambda 1 times 1 plus 0 plus 0 plus 0, just 2 zeros, is equal to 0. Let me write out the zeros actually. That's maybe more instructive. The second row corresponds to the equation 0 plus 2 lambda 2 plus 0 equals 0. And the third row corresponds to the equation, actually, what did I do here? Just a second. Yeah, so the third row corresponds to the equation lambda 1 plus 0 minus 2 lambda 3 equals 0, right? And you can see I can solve this system immediately. This immediately yields lambda 1 is 0. This immediately yields lambda 2 is 0. And then if lambda 1 is 0, of course lambda 3 is 0 as well. Right? So the only possible conclusion, lambda 1 is lambda 2 is lambda 3 is 0. I didn't even look at the fourth one, right? So this here is the fourth equation. I don't even need that. The first three already suffice to get an immediate solution. And of course, it will solve the fourth equation as well. Setting everything to 0 always works, but I don't even need to touch that one to get my solution. Right? So my point here is the pivot elements will do, and they will always yield that same solution, 0, 0, 0. And the reason for that basically is that we have these 0 blocks down here. Right? Those make sure that there are sufficiently many trivial equalities that just set one of the lambdas to 0. Right? In this case, I have 2 of those. And then, well, the third one is determined because all the other lambdas are 0 already. I can't do anything more with that third lambda. Right? This is why this works. And the same, of course, is true for the columns. Even simpler to see if I look at those. Yeah, you can immediately see zeros here and here. We'll make it simple to see that the only possible solution can again be 0, 0, 0 for the lambdas. And remember, my claim only includes the columns with pivot elements. So I'm specifically excluding this column here. If I include that, then it's not linearly independent anymore. So this is a column that is not necessary. Right? But the first three with the pivot elements, those are linearly independent. Question? Why is everything solved in column form? Just because I like column form better. You could also do it in row form. Really, it doesn't matter. All right, that much about linear independence. And that brings us to the final chapters. Basis and dimension. But before we do that, maybe one more little quiz. Yep, let's do that. Let's switch on Tweetback once again. True or false quiz. You hopefully found out by now that I like true or false quizzes, so those are going to be on the exam. Every set that contains only a single vector is linearly independent. Is that true or is that false? Any vector space you like, pick any vector from that vector space. Is that always a linearly independent set or not? I'll give you 30 more seconds to think about that. All right, so most of you said this was true. Every set that contains only a single vector is linearly independent. Why would that be the case? Any argument to back you there? Or maybe any one of the false claims does have a counterexample? Yeah? Yep, so I hope I got this answer correct. Where's my notes for today? No, last time those are my notes for today. Okay, so what you say is, let me just write it down, quiz here. What you say is if my set consists of just the zero vector, and that is included in every vector space, so I can always take that. Is that linearly independent? Well, obviously it's not, right? Because I can produce the zero vector, for example, by multiplying that by 2. Right? So I can, this is my lambda here, and this is not 0. So there is a linear combination of that vector that produces 0. That is not trivial. So that means this set here, this is a linearly dependent set. And you also said this is the only exception, and of course you're right. Every non-zero vector is a linearly independent set on its own. All right. Well, now that we've seen that, so one single vector might still be linearly dependent. Let's take a look at a more complicated case. Let's say we're looking at a set of at least 2 linearly dependent vectors. Can I then find a subset that is linearly independent? So if I have at least 2 vectors that are linearly dependent, is there one of those that on its own will be linearly independent? And I do hope the answer is more or less clear. Let's give you 20 more seconds. All right. Let's take a look. Oh, just a second. I need to switch that. All right, most of you said true, and we basically answered that one already. We said that if I have a set that just contains one vector, there's basically 2 possibilities. It could be the zero vector, then it's linearly dependent. It could be a non-zero vector, then it's linearly independent. And of course, if I have 2 vectors in the set, at least one of those must a vector that's not the zero vector. I can't just take that. Right? So the answer is true. All right. So maybe let's take a quick look at some of the questions before we get to the last slides of this week. First question I can see here is, does the solution space of non-homogeneous systems of linear equations, is that a linear subspace as well? And the answer is usually not. Maybe the zero is contained in that set, in the solution set, even if you don't see it right away. That's usually not the case. So if I have an inhomogeneous system of linear equations, usually the solutions don't include the zero vector, so it's not a linear subset, linear vector space. But it is a translation of vector space, and we've just seen that, right? So you can solve the homogeneous system, and then a solution set is just a translation of that. So it's almost a vector space. How did we know it's rank 3? I'm not quite sure what example you're talking about here. With that rank 3, is the person who asked that in the room? How do we know it is rank 3 and therefore must be a solution? Doesn't seem to be the case. Maybe you could clarify that and I can take that question later. And then there's an organizational question. Will we get more practice sheets and exercise problems aside from the weekly problem sheets? What we will do, well, there's two things. I already promised I'll give you the last exams that I did for this course. I'll upload those at some point, so you can take a look at those. We already discussed some of the exam problems, and we will discuss more of them, so I guess by the end of the semester you'll also have solutions for all of those. And we'll also use Moodle to do some electronic quizzes on there to give you some more problems to work on. We'll probably do this, I don't know, 2 or 3 times during that semester, whenever we have reached a good point to do so. I'd say maybe 1 more week and there should be a good point to try first quiz. All right. So let's go on. Basis and dimension. And once we're through that, I hope we have almost all of the definitions that I've been using all the time without actually telling you. You will find that I've already talked about dimension of certain spaces, and now let's see what that actually is. So we talked about sets that span a certain space and are irredundant, in the sense that removing any vector from that set will yield a different span. And that is basically what a basis is. So given any vector space V, we'll call a subset of the vectors a basis if those vectors span the whole space, so they generate V in a way, and if that B is irredundant. And irredundant means the set is linearly independent. I can't replace any vector by a combination of the others. Okay, that's what we call a basis. So that is, in a certain way, the most compact way to describe a vector space. Just write down a basis and then say, well, the vector space is whatever that basis spans. And it's the smallest possible description because leaving any of the vectors out will create a different space. And then I say the cardinality of such a set, any basis, that is what I call the dimension of a vector space. So in a certain sense, that is a measure for the richness of that space, right? How complex is that space? How many different directions are in that space that are independent of each other? That is what I call the dimension of that space. And again, quick convention. We already said the empty set spans the zero space. And we'll also assign that a dimension. The dimension of this set here is 0, and we'll consider that a basis of the zero space. That's simply because we can't use the set that just contains a zero vector because it's not linearly independent, right? So that's why we want to consider this empty set here as the basis of the trivial vector space. It just consists of one point. Okay, let's have a look at R2 once again. So we've talked about the different vector spaces of R2 already. Obviously, if I take just the origin, the basis for that is the empty set. We just said that. So the next level would be a line through the origin. That's a subspace of R2. Now, what is a possible basis of that subspace? Well, I can generate that set by any vector that is on the line, right? And is not the origin. So for example, let's take this, right? So that is the vector v. Then the span of v will be my orange line. We've discussed that already. And of course, that set is also linearly independent. So this is the basis for the orange space. And the other possibility in R2 could be to generate the whole space, right? So now I want everything, the whole plane. How do I get that? Well, I could again start with one line. Well, let's take this here, v. And we've seen already that this vector generates the linear subspace given by that line. So that's not sufficient to generate the whole space. We need to add another direction. And let's take this one here. Right, so this generates on its own. I would generate this line here. And taking those two together, let's call it W. We have already seen that V and W, so those two together is a basis for R2. We have seen that they generate R2, and they are linearly independent because none of them is a multiple of the other. Okay, so in R2, this is pretty simple, I hope. You just need two different directions. Right? If they're on one line, of course, they will not generate the whole space, and then will be linearly dependent. So don't tick off any other boxes, but any two different directions will work. This is meant to be V and W. V and W. Sorry. Okay? And of course, I could go on in R3. Again, just taking one vector will generate the line in that direction. Taking any two vectors in R3, like this one here, these two here, sorry, those will generate the whole plane, right? So this is this vector space here. So that would be a two-dimensional subspace of R3. And if I take a third one, which I don't have, like that, I will generate the whole space. Yeah? So this is three-dimensional, as it, of course, is expected to be. Okay? So in R2 and in R3, the lines through the origin are the one-dimensional subspaces. In R2, the plane itself is a two-dimensional subspace, and it doesn't get higher than that. In R3, the planes through the origin are the two-dimensional subspaces, and then there is R3 itself, which is three-dimensional. And of course, if you get to R4, R5, and so on, you have higher dimensional subspaces in that hierarchy. All right. One quick remark, but I'm not going to show that. Of course, that definition here, it's crucial for that definition to make sure that all bases actually have the same cardinality. I didn't prove that, and I'm not going to. Well, I can do if you want to, just let me know. It's a very nice proof, actually. But I just wanted to let you know that that can actually be shown, right? Okay, and now going back to the systems of linear equations, what does that tell us about our systems of linear equations? Well, if I have a homogeneous system of linear equations in n variables, what is the dimension of the solution space then? Well, you will remember that with these systems of linear equations, we usually have, let's say we have a couple of pivot elements here. Right, this is our echelon form, and then we might have some more rows. Right, so here's another row, column, here's another column. And those don't have a pivot element. And you remember we said, well, those correspond to free variables. So in this case, those variables are the free variables. And for every choice of the free variables, there is a new solution. And we solve for those variables where the columns contain a pivot element. Those are determined by the choice of the free variables then. So the intuition that you hopefully have at this point is the dimension of that solution space is determined by the number of free variables. Those are basically the directions that I can move freely. And we'll see an example later on where hopefully this becomes more clear. But just to state that theorem, that is exactly what is happening, right? So remember, the number of pivots is the rank. So the number of free variables is number of columns minus the rank, n minus the rank. So this is going to be the dimension of my solution space. And from this point on, I'll usually write solution spaces as span of some set of vectors for the homogeneous case. All right, let's look at the examples where this should hopefully become clear. So here is a system of linear equations, similar to the one that I've just shown you. In this case, we only have 2 pivot elements. We have 5 columns altogether, so that means there's 3 columns that don't have a pivot element. So the rank is 2. And that means the dimension of our solution space should be 3. Number of non-pivot columns, number of free variables. Well, let's see if we can compute a basis for that solution space. Now we do that just as we always solve linear systems. So we first say here's the non-pivot columns, so those are the free variables. Let's call them x3, x4, and x5. And then we take these equations here, the second one, solve that for x2, and the first one, and solve that for x1. And then this is what the solution looks like. We get this x1 here as our first coordinate. We get this x2 expression as the second coordinate. And x3, x4, x5, those may be chosen freely, so just put in any value you like, x3, x4, x5, right? So any real number yields a solution. And let me rewrite this by collecting all the x3 coefficients, all the x4 coefficients, all the x5 coefficients. For x3, we have 2 here, we have -1 here, we have 1 here, and we have zeros in those 2 rows. For x4, we get a -3, this here, a +4, a 0, a 1, and another 0. And then for x5, we're no x5 in the first row, so there's a 0, 1 here, 0 here and here, and a 1 in the last row. Okay, and you will see this is nothing else than the set of all linear combinations of those 3 vectors here. Right? So the x's are now my coefficients. And that means I can just abbreviate this and write, well, this is the span of those 3 vectors. Question, is this a basis? So is it irredundant? Are those linearly independent? Well, if we take a closer look at them, specifically at the rows that correspond to the free variables, the last 3 in this case, right? Yeah, you'll see for each row there's always one entry and 2 0 entries. So if I try to combine those together, let's write that down just for once. Right, if I want to compute, I want to have a linear combination of those 3, 0, 1, 0, 0, 1. And I'll just write that here. So that linear combination has to yield 0. And I want to find out if there is a possibility of doing so and not setting all the lambdas to 0. Well, then I can immediately see the first of those free variable rows, so the third row actually, this one here. This immediately yields the equation lambda 1 is 0. This is the row that corresponds to my second free variable. This immediately yields the equation lambda 2 is 0. And of course, the same works for the last row that corresponds to my last free variable. Lambda 3 is 0. Right? So for each of those free variables, I always have a row that contains just zeros and one single one entry. And if I try to come up with a linear combination for the 0 vector, these rows will always yield equations like that. And that's why this is always linearly independent, right? If I just use one vector for each free variable, in this way, I always get a basis. Okay, so this is not just a generator, this is the basis of my solution set. Okay, and if you do it this way, you can be sure you always get a basis. Okay, I even did that here, so let's scroll over that. All right, questions at this point? Yes? Yeah? Yep, you. So linear independence means there is just this one solution of setting all the lambdas to 0. One is not enough, all must be 0. If there is a different way, then they're linearly dependent. This one? Yeah. The first and the second row, though, it's not immediately clear from those rows what the solution might be. Right? But if I just look at the last 3 rows, those already give me one unique solution for my system, right? There can't be another solution. Of course, I'd have to make sure that actually that solution also satisfies the first and the second row. I didn't even look at those. But if that solution is all zeros, then of course, well, setting everything to 0 will always yield 0. Right? We can't go wrong with zeros everywhere. Yeah, I'm just pick the rows that make it easy for me to solve the system. Yeah? Yep, you.
So if we write this back, do we always need to, or do we need to reduce it to a base inside the record? For example,
So the question is, do we always have to give a base of the solution space?
right.
Usually, yes. So usually, from now on, I will not just be asking for the solution space, but instead I will be asking for a base of the solution space.
So for a homogeneous equation system, later in this exam, we define it as S plus U.
For an inhomogeneous system, of course, that is usually not possible. It's not a vector space, so it doesn't have a base, strictly speaking, right? What I could ask for is the base for the homogeneous system and then a solution space of the inhomogeneous system, which, of course, you can then combine using that base and add a particular solution. Yeah, but mostly from now on, I mean in applications, of course, but in theory, we mostly work with homogeneous systems from now on, because inhomogeneous systems is just the same thing plus a translation. And the theory is just nicer for the homogeneous case. And it's the same anyway, so why bother? All right, any more questions? Good, that does not seem to be the case. So let's have a quick look at the last homework problem before we conclude that for today. I need to switch on the presentation here, yeah. So exercise 3.3, where do I have that? So given a system of linear equations, I think that was it, right? Yeah, given a system of linear equations, the question is, what is the dimension of the solution space? And the second question is then to determine a basis for the solution space. And I'd like to ask you for the dimension. And once again, I'd like to see how hard you found that problem. So I'll give you 30 more seconds to cast your vote. Because you all did this at home. All right, so let's take a look at the first question. What is the dimension of the solution space? Most of you are saying 2, and that is the right answer. So the dimension of the solution space is 2. And let's see how hard you found that. Oh, that's a nice distribution. So some found it easy, some found it hard, some found it medium, anywhere in the middle. So basically points everywhere on that heat map. All right, we'll see a couple more examples like this. But I'd say it's probably not worth the hassle starting one of those today. So we'll do a few examples of that kind on Thursday. And if you want me to discuss that homework, then please let me know. Otherwise, I'll just go on with similar but other examples. So that's it for today. Have a nice evening, and I'll see you on Thursday.